Hi, I'm Naoma McCall. Thanks for coming to listen to this talk. I'm going to be talking about more seismic data and lava tubes, specifically at Skull Cave and the La Corona lava tube in Lanzarote, Spain. Oh. All right. So the previous speakers have done a great job giving you a primer on lava tubes. And if you're in the session, you probably know a lot about them already. But in case you walked in here and you want to know why we're talking about lava tubes, we've got these structures on Earth, but we also find them on other bodies such as the Moon and Mars. And they are of interest to us because both for exploration purposes and for future science missions, they can provide shelter for solar radiation. So we've got an image of a mock-up of a module inside a lava tube, and so that can shield astronauts or even electronics, and they can also preserve water ice or other volatiles. So basically, they're really important both for exploration and for science. On Earth, these structures tend to be rather shallow, about 10 meters or above in the subsurface, and on the Moon, they can be a lot deeper into the 100-meter range. And so, as Lyndon touched on, seismic reflection can be a really useful tool for detecting and characterizing these tubes, because reflection can resolve structure hundreds of meters into the subsurface. So I'm going to go over two field areas that we looked at, one being the La Corona lava tube in Lanzarote, Spain. This is off the coast of Morocco in the Canary Islands, and Skull Cave in Lava Beds National Monument in Northern California. So first we'll talk about the La Corona lava tube. This is a really cool tube. It's very long. It's over 8 kilometers long. It goes both onshore and offshore. And the diameter is up to 25 meters. And because it's a very long tube, the depth ranges. So from below 5 meters of overburden to 30 meters. And we see this really deep overburden because this tube, unlike some of the other lava tubes that form via an overcrusting channel, this tube is formed via deep inflation. And so this is where lava flow takes advantage of a weaker layer in the subsurface. So there's like a cinder-like inception layer. And so we can see that both in this diagram, as well as this is a picture from inside the Corona tube. You can see the red layer in that middle photograph. The far right photograph is just a picture of us in the field. So you can see some geologists for scale that this is a really large lava tube. So it's really exciting to be able to go there and study it. Also, most of this tube has been LiDAR scanned of the interior, and the authors of that study were kind enough to share their LiDAR with us, which helped inform our survey as well as help us with the data interpretation. So we were able to collect 4 transects at La Corona. If we look at this aerial image, we can see kind of like two overriding colors, where we've got the dark land and the light land. So the light land is basically this really rocky lava flow, and the darker areas are farmland. And so when we got there, we saw that there was no way we could get a geophone into the ground and the lava flow. So our lines focus farther away from the coast. So the small square shows our 4 transects, and the larger inset shows the LiDAR. The blue colors are more shallow and the red colors are deep. So we've got 4 transects at a range of depths, and we had a very dense geophone spacing. So both our receiver and source spacing was 0.5 meter. And this is to increase our resolution of the seismic survey. So we've got a couple of pictures of us in the field there. This was just done this last May, so really recently. And so we can see just how close together the geophones and the hammer hits are for the survey. We process the data using the Cruise MATLAB toolkit. So that workflow includes things like a radon transform, a bandpass filter, elevation correction, muting out the airwave, normal move out, stack, and migration, which Lyndon kindly touched on. So this is a look at some of the data. This is some preliminary processing. So this first survey, basically our 4 surveys start shallow and go more deep as we go further from the volcano of La Corona. So this first tube is 15 to 11 meters deep, and we can see the LiDAR here shows the cross-section of the tube. So this tube is asymmetric both in the cross-section view and a long section. So when we've got this irregular shape, we're going to get a lot of scattering in the seismic data. And so we can kind of see that in our section. What we're looking at is, first we've got our migrated section that's just totally uninterpreted, and then right next to it is our interpreted section. The dotted lines show where the cave is along the section. And then I've just kind of highlighted some of these high amplitude returns that we're getting. And then these are diffractions off the cave ceiling and walls. And so for a tube that is has this irregular shape, we're going to get a lot of diffractions. And luckily we've got this LiDAR so we can see just what the tube looks like. So going to our next transect, this one's deeper. So this one's about 22 meters of overburden. And if we look at where we know the tube should be, we can see a diffraction at the height of where the cave ceiling should be. So that's really cool. And similarly for our next transect, which is about the same overburden, a little bit more. Now we're at 23 to 24 meters depth. And again, we can see this diffraction off the cave ceiling where we expect the lava tube to be in both time and space. Our last section, this is the deepest section. So this one's almost 30 meters deep. This is almost the deepest part of the La Corona tube. And we see a really high amplitude return here. And so you can see that in the uninterpreted section, your eyes probably go right to that high amplitude area that I've shown on the right. And so this is really promising, but what you can also probably see is that if you didn't know where the tube was, you might have a hard time identifying it. So we're at a point right now where if we know where the tube is, we can look at our data and say, okay, we see a high amplitude seismic return there. But this is still kind of preliminary processing. So we're trying to figure out what else we can do. If we didn't know where the tube was, could we remove some of this ambiguity? So now I'm going to go to Skull Cave. So Skull Cave is shallower than La Corona. It's about 5 meters of overburden, but similar diameter. And this one is shallow and it's formed by the overcrusting of a lava channel. And it's co-located with a ton of other geophysics, including some LiDAR, which I'll show you. We had similar data collection at Skull Cave. This was done in June of 2022. So this is actually done first. But again, we had a really dense seismic survey with a half-meter receiver spacing and 1 meter source spacing. And again, we used the Cruise MATLAB toolkit to process the data with a similar workflow. And so this tube is shallower than La Corona. And so as Lyndon kind of touched on, there's sort of an ideal depth for seismic data, and 5 meters is awfully shallow for it. So detecting the tube here is a little bit more challenging, but again, we do see some high amplitude refractions off of the cave ceiling and walls. And so we can see the LiDAR of the tube here, which tells us the shape and like lateral extent of the tube. And then we can look at our section and we know where the tube should be. And again, we see a high amplitude seismic return there. So in conclusion, the seismic reflection shows a lot of potential for resolving lava tubes. However, we need to do some more advanced processing to remove some of the ambiguity so that we can detect lava tubes where we don't already know where they are. And we also want to do some processing of refraction data and some non-body wave analysis using surface waves or CODA and see if that can resolve these tubes further. So thank you very much.